Today we're going to do problem 3.4.10 for lesson 31. We are given an A matrix, A equals 1, 2, 3, 2, and we are asked to find the associated eigenvalues and eigenvectors. So an eigenvalue exists if it satisfies the characteristic equation. So the first thing we want to do is solve the characteristic equation. So the characteristic equation says that an eigenvalue is an eigenvalue for a matrix if the determinant of A minus lambda I equals 0. So we're going to solve for A minus lambda I and set the determinant equal to 0. So A minus lambda I equals the A matrix 1, 2, 3, 2 minus lambda times the identity matrix, which is equal to 1, 2, 3, 2 minus lambda 0, 0, lambda. And this is equal to the matrix 1 minus lambda, 2, 3, and 2 minus lambda. Now we take the determinant of this matrix, so we take the determinant of the matrix 1 minus lambda, 2, 3, and 2 minus lambda, which gives us 1 minus lambda times 2 minus lambda minus 3 times 2, and we're going to set that equal to 0. Then we're going to distribute and solve for lambda using the roots of the equation. When we factor it out, distribute it out and factor, we get 2 minus lambda minus 2 lambda plus lambda squared minus 6 equals 0. And then when we put this in the correct order, lambda squared minus 3 lambda minus 4 equals 0, which we can factor into lambda minus 4 and lambda plus 1 equal to 0. Therefore, our associated lambda values, which are our eigenvalues, are 4 and lambda equal negative 1. So these are our eigenvalues of A. Now the next step is to find the eigenvectors associated with each eigenvalue. So we want to find the eigenvectors associated with each lambda. So we use the equation A times the vector V equals lambda times V. And if we're going to solve for the first vector, we're going to use the first lambda. So our A matrix is, again, 1, 2, 3, 2. And then we're going to solve for vector 1. And that's going to equal our lambda 1 times vector 1. And we'll say that lambda 1 is 4. So then 1, 2, 3, 2 times the vector v, which will make v1 and v2, is going to equal 4 times v1, v2. And then when we come up with the series of equations for this, we get 1v1 plus 2v2 equals 4v1, and 3v1 plus 2v2 equals 4v2. And then we can rearrange and solve for v1, and we get that using the second equation here, we have equation 1, equation 2, if we use the second equation to solve for v1, we get 3v1 equals 2v2, and v1 equals 2/3 v2. This gives us a eigenvector of 2/3 and 1. And our lambda 1 was 4. So our eigenvalue is 4, and our eigenvector associated is 2/3 and 1. Now we're going to find the second eigenvector, and again we use the same 1, 2, 3, 2, and then we use vector 2, which we're trying to find using our second eigenvalue of -1, and then our second vector, which we will again call v1, v2. And that gives us two equations. Equation 1, which would be 1v1 plus 2v2 equals -1v1, and equation 2 of 3v1 plus 2v2 equals -1v2. And then the same process as we did before. And using the same process as we did before, we get, using the second equation, we solve for v1, and we get 3v1. 3v1 equals negative 3v2, which gives us a v1 equal to negative v2. And therefore our associated eigenvector would be vector 2 equals -1 and 1, with the associated lambda 2 equal to -1. So therefore our associated eigenvectors and eigenvalues for this problem are lambda 1 equals 4, with vector 1 being 2/3 and 1, and lambda 2 equal -1, with our eigenvector 2 of -1 and 1.